So fluid dynamics. Have we started the dynamics also? Did I give any explanation to the dynamics part in the last lecture? Yes or no? Hello, hello, 1 2 3, 1 2 3.
Sir,
Last lecture. So let's begin with the dynamics. So what do we mean by fluid dynamics? So we say that when the fluid is in the relative motion with respect to the surrounding, you can say solid surface or surrounding medium, you can say not surface. Then we say the fluid is in dynamic system, dynamic state. For example, if you take a bucket of water and if you start running, then of course we cannot say it's a fluid dynamics because the water is not moving the relative to the immediate surrounding, which is the bucket. But if you pour the water out of the bucket, then definitely the water is in a relative motion with respect to the immediate surrounding, and we term is a dynamic state. So for dynamics, it is necessary that the given fluid, which is liquid, which may be liquid or gas, must be performing some relative motion with respect to the immediate surrounding. So when fluid moves with respect to immediate surrounding, then it is said to be dynamic state. So in dynamic state, we define certain features of fluids. So there are two types of fluid flow. First is called streamline, also called laminar, and second is called turbulent. Now all the mathematical details that we are going to study will be meant for the streamline flow of liquid. So why the streamline flow of liquid is interesting one? The reason is the moment the flow becomes streamlined, it becomes predictable in nature, which means you can actually guess the motion of moving fluid in a given volume by knowing some parameters. So let's say we have some tube and some liquid is moving through this tube. So streamline is a concept. So if I convert this volume into elementary tubes, imagine instead of one big hole, imagine we have a tiny holes, and every tiny holes moves parallel to each other, reaching the other end. So these are called the stream tubes. So stream tubes itself is a small imaginary tube, and inside this single stream tube we have infinitely streamlines. So you can think of stream tube as a collection of streamlines. And the streamline flow is basically a flow in which the fluid can be conceptualized as a collection of stream tubes, which in turn can be conceptualized as a collection of streamlines. And these streamlines never ever intersect each other. That's the beauty. So they always remain parallel to each other. So they never intersect. Now, because of the property of not intersecting, they follow certain rules that we are going to discuss here. So if we have a tube of varying cross section, so they say the cross section is not constant, and if we have a streamlines, so these streamlines will have to also get narrower as the tube becomes. But no matter what, streamlines never intersect each other. So they maintain their non-intersecting properties. Okay, maybe I can do. So none of them will intersect. They can become narrow. They can become like widely separated, but they cannot intersect. And the moment this kind of situation happens, the liquid particle. So I have discussed about the liquid particle in the very beginning. So we streamline is like a predefined path that you are supposed to follow, and once you predefine the path, the liquid particle will follow this path no matter what. So when it is here, it will have some velocity v in this direction. The moment you come here, your velocity will change to some value v dash in the other direction. And what is interesting that every particle passing through the first point will have the same velocity v all the time, and every particle crossing the point 2 will have the velocity v dash all the time. It means every point you select will have a unique velocity in this space. So particle will come and go, but the point will not change its property, which means the entire volume of this tube through which the fluid is in motion will have well-defined velocity vector, and such a space is called velocity space or velocity field. So you might have heard about the electric field, magnetic field, gravitational field. So in fluid dynamics, what we define is called the velocity field, because velocity is well defined for every point. So fluid has to only pass through those points with the recommended velocity, which means it is like, I mean, you're driving a car and the speed limit is decided by the location. And if for the streamline flow, it is necessary that every vehicle passing through the given point or given junction must acquire the velocity which is already mentioned near that junction. So if you have seen the speed limit put on the road, that you must drive at 30 km per hour or 40 or 60. The whole idea is if everyone will follow the same speed, then the vehicles can move streamline without getting congested, without creating any traffic. But that is not the case in the real life. So we do get the traffic. Similarly, in case of fluid moving through a tube or any cross section or any volume, the moment we say streamline, it means every point of that volume will have well-defined velocity. So every particle crossing a given point will have a unique velocity. Are you getting my point? What I'm saying? So in case of streamline, what happens? The velocity becomes the property of the space, and particle crossing a particular coordinate of that space will have a unique velocity. So when you will pass the particle which is chasing you, when it will cross the same point, will always cross with the same velocity. So the space will have the well-defined velocity. Particle has to follow it, and when it happens, we say it is a streamline flow, and the entire space we say velocity space. So this entire thing, entire volume becomes velocity space. So in streamline flow, what happens? Velocity becomes property of space, and every coordinate of space will have well-defined velocity. And that is why the entire volume is called velocity space, and velocity will behave as a vector field, and velocity will behave as vector field. So that is the property of streamline flow. So in the case of streamline, the moment I say this is a cross section, then this cross section will have its unique velocity, which is determined by the streamlines passing through this particular cross section. You can also see that the number of streamlines cannot increase or decrease. They can only get closer and go farther depending on the shape. So the number of streamlines remains constant, and the count of the streamlines through a given cross section is called flux. And because this is the flux due to velocity space, so in physics we call it velocity flux. So flux is the count of lines, or you can say streamlines passing through a given cross section. This is the cross section through which the streamlines are crossing. So how many of them are crossing? I mean, some you can assign some relative number. So the number of streamlines crossing a cross section is called velocity flux. So let me define separately. And this is very much similar to the idea of gravitational flux and electric flux, which you will study very soon in the class 12. So velocity flux, you can think as it is the number density of streamlines passing through a given cross section of fluid flow. Now these terms are confusing, like number density, and why we need to mention it. So we cannot count the exact number of streamlines because it is technically infinite. But it is same as like counting the number of hair strand on your head. So of course you cannot count how many hair strand is on your head, but you can say at least that okay, someone's the the density of hair is more per unit area than someone else, and someone who is bald will have almost no density of hair per unit area. Something which is uncountable can have a relative comparison, and that's why we use the word density, which is like the relative comparison of the infiniteness. So maybe everyone will have infinite, but someone's infiniteness will be bigger or smaller than someone else's infiniteness. So we're comparing the degree of infinity, like how big that infinity is compared to other infinity. So number density is that word which quantifies the same. So everything is infinite, but still we can have some relative comparison. So for example, the number of lines of force here is, let's say, 1 million. But if you go through this particular cross section, it is still 1 million, but they are quite closer. So this density is really large compared to this density. So the number density will grow, and what it represents graphically, that more the density, more the uh, speed of velocity. Just a minute. Hello guys, am I audible?
Yes.
So you got the idea of velocity flux. Flux is what? It's the number density of streamlines passing through a given cross section. And in physics, or in especially in the fluid dynamics, so इसी का फोन आ रहा है. Sorry guys, I'm getting call after call. Okay. So in this particular chapter, the velocity flux is actually designated as a discharge rate. So we call it discharge. And the symbol that we use for is Q. And discharge is also called the volume flow rate. Like how much liquid will cross the given cross section per unit time. So we call it volume flow rate. And this is same as velocity flux. Everything is same. So all are name actually. You can say discharge, you can say volume flow rate, you can say velocity flux, everything is same. And the definition is V dot D. So if we have a cross section and if we have a streamline flow, generally this will reduce to simply V, or normally we write AV. And we can prove it. I mean, it's very simple. So if you read any book, I mean, of course, they will not mention everything else. So they only call volume flow rate. This formula is from the concept of flux. And because here we have the velocity as a field. So if you study later on that, the flux is defined as a field vector dot area vector. So this is the general definition of flux in physics. So it can be electric field. So we say electric flux. If you change the field to magnetic field, we call it magnetic flux. If you change the field to gravity, we call it gravity flux. And here we have the velocity flux. So we write V dot dA. So you can see there is a pattern which you can easily identify and understand. Okay. So imagine we have a cross section here, and if your liquid is moving or flowing through this tube continuously, So if this is the area of cross section, if the velocity of the fluid is v, so we know that through this cross section area in time dt, the liquid will travel v dt ahead. So this volume between the two cross section which I have shown here, this amount of liquid has crossed this cross section in time dt. So the volume is equals to area into length, and therefore the d volume by dt is A into V, and this is called the volume flow rate, which we represent by the symbol capital Q, and this is also called discharge rate or simply discharge. Discharge rate. So the discharging rate is amount of volume crossing the given cross section per unit time, which we can write as A into V. And this is the case when the volume, the velocity is, you can say, constant throughout the cross section. If we have a situation when the velocity is varying over the cross section, which is the case in reality because of the concept of viscosity, if you remember. So we know that because of the viscosity, the liquid near the wall of cavity will be slow and the velocity will be fastest at the center. So the velocity graph, this graph velocity will be like this, which means the velocity will vary from center to the wall of this tube or cylinder. So when velocity becomes variable, in such case the flux, let's call Q as a flux, velocity flux, we define as V dot dA, and generally you will come across this will become V into 2 pi r dr. This is how we take the cross section if it is circular. So we go to r radius and we cut a dr, and we believe that the velocity of this radius is v, and generally v will be also a function of some r only. So velocity will vary as per the r, and you will have the answer like this. Okay, understood. So normally this will be only for the viscous liquid, this formula we will use, but for a general problem, the product of area and the velocity of that cross section will give you the discharge rate, and that's very easy to derive, and we have been doing this for a long time. So now there is a concept of ideal liquid. So for ideal liquid, it must be inviscid. So inviscid basically means which is not viscous. And definitely it must be incompressible. And it means you cannot compress it. So density remains constant. That's the idea of, and this is the assumption that we make for the ideal liquid. And because in our case the liquid is inviscid, so velocity will be same for one given one cross section. So we generally assume that one cross section will have one particular velocity. That's how we assume. So every cross section will have its unique velocity. and if the cross sections are same, velocity must be same. So we look for the cross section area. So in case of fluid flow, until we cannot change the area, we cannot change the velocity. That's the idea. So one particular cross section cannot have two separate velocity. So now if we have a tube like this with two separate cross section and then there is a variation. If you go from here to here, anywhere, you cannot have two different velocity because the area is same. Velocity is bound to change. I mean, bound to be same. Now this is the area where the velocity will change continuously. But the moment you reach here, once you reach V dash, everywhere it is V dash. And here it will change continuously because the area is also changing continuously. So of course, but for one unique area, it will have unique velocity. V unique, whatever. So this is our assumption that our liquid is non-viscous and inviscid, and because of that reason, the flow will have unique velocity for a one particular cross section. So until the cross section is not changing, you cannot change the velocity. So in case of fluid flow, the velocity cannot be changed, which means you cannot accelerate liquid. That's very interesting. You cannot accelerate liquid in a given cross section. And why it is so? Because once you create the pressure difference, it will accelerate through the change of cross section area. So for one cross section area, it will have one velocity. It is not possible that the same liquid will move with different velocity in different cross section area. Sorry, in the same cross section area. So you cannot accept velocity V1 is here, V2 here, V3 here, V4 here. This is not possible. This is not possible. It must be same. And why it must be same? You can think in this way that the amount of liquid coming cannot exceed the amount of liquid leaving. So imagine that you say that no, sir, I want a situation in which V1, V2, V3, V4 is possible. So that is possible, but in such scenario, the streamline concept will be broken down, and now the flow will become turbulent. That is exactly the case of turbulence. In turbulence, the velocity field gets distorted in a way. There is no uniqueness in the velocity distribution of space. So, for example, if you open a tap, you might have observed this. So, when you open a tap and if you let the liquid to flow, the liquid flows like this. If you open slowly, so as it goes down, it becomes narrower. Have you seen this? Anyone? So, if you have a tap, if you open slowly, you can see that the water will fall down and will become narrower as it goes down. Anyone?
Yes.
Hello, one, two. So the question is why it becomes like this? Why the cross section becomes narrower as it goes down? Because the amount of water you are giving is fixed. So you are giving, let's say, maybe 1 liter per minute is the rate of water coming out of the tap. So now, as it will fall down, the velocity will be more. So this is V2, and because it's a free fall, so V2 square equals to V1 square plus 2GH. Let's say H is the height. Okay, that will also prove in other way also. So the whole idea is if velocity will grow, we cannot change the discharge rate, because we have limited amount of water coming, and because it is trying to maintain the streamline flow, so the continuity is necessary. So product of A and V is constant. So as V will increase, A has to decrease to balance this. Understood? So Q is constant. The rate of water given by the tap is fixed, and therefore the product of A into V is constant. So as A will grow, A will as V will grow, A has to. So A2 will be A multiplied by V1 by V2. And since V2 is more than V1, A2 will be less than A1. Correct? Is this clear, guys? Why it is decreasing? So this is called continuity equation. But what is something that we don't observe even more in detail? That after some time, the water starts leaving the flow and they become discrete. It's like they start breaking down into droplets. And when this happens, because when the velocity becomes very high, so V3 is so high that it cannot follow the incoming rate. And when the velocity becomes really high, it starts breaking down. So then what you see is the turbulence. So now this is not part of streamline. The streamline is only till here. But this is the turbulence. Understood? So you
Yes,
can
sir.
see that in a single flow, we have both event happening, the steam flow and the streamline flow and the turbulent flow. In a single event, you can see both the event happening. Also, you can see that when you like burn the incense stick while doing some puja and arati, the flame or the fume, you can say, the fume rising will have a very nice texture like a steam line, but after rising certain height, it becomes turbulent because the rate at which the fume is rising and the rate at which, I mean, as you go up, your velocity is not like, of course, decreasing at the same rate. So eventually, the fluid particle, or you can say the smoke particle comes from the bottom, and the smoke particle which is at the top, they don't follow the streamline process, and they get mixed up. And you can see there is a turbulence at some top. You can all easily observe it to your home also. So you can burn any incense stick, and you can see how the smoke is rising. So initially it is streamline, but later on it becomes turbulent. Okay, and the moment it becomes turbulent, there is no mathematical relationship. So our mathematical relationship is only meant for the streamline flow. Understood? So there are many examples, of course. So streamline actually keeps the definite relation of velocity with respect to space, and the moment it becomes turbulent, there is no mathematical relationship, and that is why we study the streamline flow only in our syllabus. And the other things are very complex, and that can be only learned through the simulation rather than doing some mathematics. Okay. So with this assumption, we can go and forward. I mean, we can say something called continuity equation for streamline flow, which is a necessary condition. We say equation of continuity. So again, the continuity equation we apply for the streamline only. So if we have a variable cross section, And if the liquid is flowing, so again, if we have cross-section area A1 here and we say A2 here, and if the velocity is V1 here and velocity is V2 here, because our liquid is incompressible, so imagine the liquid only between the two cross-sections. So can we say that the amount of or the volume between these two cross-sections is fixed? Can we add more liquid between these two volumes? If the density is constant, because we are assuming it's incompressible for the, and this is the condition for streamline flow, we don't assume the variation of density. So the amount of fluid between the cross-section A1 and A2 we cannot change, which means whatever will enter from this cross-section in a time dt, the same must exit from this cross-section in the same time dt, because if this is not the case, then the net volume within this will change, which we cannot consider as per the assumption. So the whole idea of continuity is that the liquid is incompressible, or even the fluid we assume as incompressible. We're not going to change its volume and density, and thereby they're following the continuity equation. So the discharge through this cross section is same as discharge through this cross section. So Q is a constant quantity. Q is a constant quantity, and because Q is equals to AV, so this relation will be true all the time as long as the streamline is concerned, as long as the compressibility of fluid is ignored. Even for gas, although we can compress it, but in the streamline flow, they will not change the density in the due action of flow. So when the cross section will become smaller, the fluid will try to move faster, okay, in order to maintain the density. So it is not like that they will get compressed in some part of the volume and they will not be compressed in some other part. So that's not the case. So Q equals to A1, V1, A2, V2. And this is not just true for only one tube. You can, if you have a tube in which suddenly we have multiple cross sections, and this is generally the case of the arteries in the human body. So if the liquid is moving, let's say this is the blood flow. This area is, this is V, and suddenly you have multiple arteries. You can see of varying cross section area A1, A2, A3. So what remain constant is the Q. So now this Q, the discharge will spread through all cross section, and each will have some velocity V1, V2. The same is for the drainage system. The same is for the water distribution in a city. Okay. So the main supply will have the fixed value of Q, and they know exactly that how many pipelines they can open for this Q to be maintained across various cross section. And that is how in city like Mumbai, which is a metropolitan city, they have some timing for different locations so that they can maintain the discharge flow across the different pipelines for a given interval. If they open all pipeline at the same time, probably it will be very difficult task for them to maintain the flow rate, and therefore some pipeline may not receive water at all. Things will be in a very bad shape. So from the continuity, what we can say, the net discharge rate cannot change. So the A1 V1 plus A2 V2, because it is the division of the flow. So the sum of all division must be equal to the bigger one, AB. And this we call the equation of continuity. So whether it's a human body, arteries, veins, so what happens that when the the fat gets accumulated in the arteries walls, the cross section decreases, and by virtue of decrease of cross section, the flow gets hampered. Now, in reality, if the blood we assume as inviscid, which is not the case because blood is very thick in nature, and as the blood thickness will like thickness, or you can say it becomes more denser, the viscous effect comes into picture. So, what happens if you narrow down the wall of an artery? The viscous effect becomes very dominant, and that will reduce the blood flow. And if the sufficient blood will not reach, then certain action will be hampered, and there is a high chance of something called heart attack. Okay. So the fluid dynamics is working inside the body, and of course, everything is following the basic principle of either the Bernoulli equation or the Poisson equation. Okay, so for the blood to flow through the tiny veins, because of viscosity, their natural speed decreases, which is in a way very good because the veins are very delicate thing, and if the flow is really high, then it may affect the veins in multiple ways. So you can imagine the human body is a complex network of pipelines, and the complexity of the human body is infinitely more than complexity of any city or any metro. So now we can come to the other part that is called. So we can also take the example of tap, but that's we have done. So now what is being governed in the fluid flow? Which formula we follow? Which equation we follow? So we have something called Bernoulli equation, Bernoulli theorem. So what Bernoulli theorem says? So first I will add the statement, then I will prove it using the laws of motion. So according to Bernoulli theorem, the sum of pressure head, kinetic head, and potential head along a streamline remains constant. Okay. So the concept we will discuss later on. What is the meaning of head and how we write it. So the sum of these three things, like P by rho G, so this is the statement of the Bernoulli uh, theorem that if you follow a particular streamline, this is the some random tube, and if you pick some streamline which is part of the tube, and if you walk through this streamline, so no matter where you go, if you draw some reference line, then this is called the H actually, or the height. So the height is called potential head, and if your velocity is here v at any given, let's say in general v you are there. So if the velocity of the particle, the fluid particle at this location is V, then V square by 2G is called the kinetic head. And because it is a liquid, so at this point there must be some pressure. So the pressure at this location upon rho G is called the pressure head. And what it is saying that if you go here, the pressure may become P dash, velocity may become V dash, and H may become H dash, but the sum of these three will never change. So which means P by rho G, V square by 2G plus H is same as P dash by rho G, V dash square by 2G plus H dash. So individually they may change, but their sum always remains constant, and that is the statement of Bernoulli theorem. So we'll prove it mathematically how why this is true. There are two methods to prove, but before that, let me tell you the Bernoulli theorem is the consequence of work energy theorem. So is a consequence of so Bernoulli theorem is the consequence of work energy theorem, which means in a moving liquid, what we apply is the work energy theorem, and the concept of work, why we and how we define, we'll see very soon. So we assume that the liquid flow is non-dissipative event. It means when the liquid is in the motion through a tube, because of the assumption it's inviscid, the viscous drag or the friction is assumed to be absent, and because of the drag force is absent, absolutely there is no loss of energy, and therefore in the work energy theorem, uh, the work and the change in energy will be always equal because there is no loss actually, and this derives the formula on the left side. So we have to just write the work energy theorem formula, and once you do it, you will come to know this is constant. So we'll see the multiple perspective of derivation and how to derive it in multiple ways. So I will teach you the derivation in a very different way, which simply uses the laws of motion, and it has nothing to do with the energy conservation, because we know that every question in which energy, if there is no dissipation of energy, so the question which you can solve by the energy consumption, you can also solve by the laws of motion, right? If you know the path and all. So let's see the derivation part. Derivation. So imagine we have a two-dimensional plane. The y represents the vertical and the x represents the horizontal. And there may be some random tube. So I might not be drawing the entire tube, just a part of tube. So it's a complex circuit in which we just take one piece of it, and this tube is of some random shape, and within this tube we consider some streamline. Let me make it thin. So this is the streamline, And if this is streamlined, then the liquid particle will trace this path. So to get the sense of the liquid particle, so this is a tiny cylinder, and imagine the length of this tiny cylinder is ds, and the cross sectional area you can assume as dA. So ds is the length and dA is the cross sectional area, and now we need to draw the FBD. So it may have some velocity at that instant, but let's leave it. So what we can write is the one of the force will be gravitational pull, and we can write as dmg, because it is part of a liquid, so it will have some pressure here. Let's call the pressure as P. But on the pressure on the other side is, let's call it P plus dP. So some force will be acting this way, which is again due to the pressure only, so you can call it normal. And why it is so? Because it is balancing. So my fluid particle is not moving up and down, it's moving along the streamline. So we can say the net force normal to the streamline must be balanced, right? So the net force, and of course, let me draw a tangent along this line. And why I'm drawing this tangent, the reason is obvious. I want to know this angle theta so that we can write something mathematically. So now if you look at the perpendicular force to the streamline, this must be 0 because of the equilibrium condition. And this will give you the answer like dn equals to dmg cos theta, as we know. This is theta. I hope you guys remember this, but this is of no use. What we need is the net tangential force acting on the fluid particle, which I have taken in the shape of a cylinder. This must be equals to mass into tangential acceleration, isn't it? This is correct? Yes or no? Can we write like this? Hello, hello, hello. 1, 2, 3.
Yes, sir.
Am I audible, guys? So can you guys substitute the value of a net force along the tangent? Can you substitute? And if you substitute, what will be the answer? Like, what will be the value of the substitution? So looking at the diagram, tell me the answer. What I should write here? So this particle is moving along this direction, right? Towards right. So what is the net force acting in that direction? It is PdA. Let's say that dA is the cross-sectional area. PdA is the push force towards the motion, minus P plus dP into dA, because that is the pushing backward. So net force along the tangent is this much. So you can see that it is the pressure which accelerates the liquid. So PdA minus P plus dP into dA, this must be equal to what this is equal to? dm into AT. Oh, sorry, one thing I missed. And one more force is acting down the plane, which is minus dmg sine theta. The gravity is also will have the component, and this must be equal to how much? Dm into tangential acceleration. Is this clear to everyone? Check this out. Does it make any sense?
Yes.
Okay. So once you solve it, P dA will cancel out. So minus dP into dA, the mass we can write as density into volume, and volume we can write as plus into ds equals to rho dA ds into tangential acceleration. So dA will cancel out. So what we're left with is minus dP minus rho ds sin theta equals to rho ds, and tangential acceleration we can write as v dv by ds by definition. So what you can see that minus dP minus rho and ds sin theta we can write as dy, if you remember. So we have done this many times. This is ds. If this is theta, this is ds, this is, and dy is ds sin theta, right? So you may write like this. So this is equal to rho v dv. Understood? So dp plus rho v dv plus uh, rho dy equals to 0. So this is called Euler's equation. So if you go for marine engineering or if you do mechanical, then you will study the Euler's equation. And if you integrate the Euler's equation, what you get is called Bernoulli theorem. So integrating both sides, what we get is dp plus rho v dv plus, I think I have missed something, g, yeah. Hmm. And if you integrate constant, what will, as is 0, you get constant because constant differentiation is 0. So you can say this is constant. And that is how we can write P plus if density is constant. Now look at this. The Euler's equation will become Bernoulli equation or Bernoulli theorem only when the density is fixed. Otherwise, you cannot integrate. That's the problem. So assuming density is constant, we can take outside and V dV becomes V square by 2. And again, rho is constant, G is constant, so dy becomes Y. And this is called Bernoulli theorem. So this is a different way of deriving. This will study only in the BTech. If you go to IIT Bombay only, so mostly it is taught in some of the IITs. So now what we have is the pressure plus half rho V square plus rho Gy is constant. We need to understand that the third term is because of the reference taken. So see, I have taken the reference. This is the If I choose the x-axis as the reference, then the rho g y is the things from the understood. So now if I divide by rho into g, this will exactly become like this. And the rho and g is constant, this is another constant. And this is the statement of the Bernoulli theorem. And this is called the pressure head. This is called velocity head, kinetic head. This is called the potential head. So potential head is by virtue of the distance from the reference. So it may change depending on how you choose the reference. Why? So third term is not something of great importance because we can choose in a way to eliminate also. So we can choose the reference at the level of. So if I know somehow that if the streamline is horizontal, and if you choose any reference, it means the y always remains same. So it is good to choose this as a reference itself. In that case, we're not supposed to write the third term. Okay. So there are some different ways to interpret. So one is the like head means height. So you can think like dimensionally everything is representing height. Okay. The other way of thinking is energy density. So in case of pressure, if this is the cross-sectional area, this is the pressure P, and let's say this goes from here to here, dx. So we all know work done is defined as force into displacement, and here the work is being done by the pressure which is in the liquid. So the force on the cross section we can write as pressure into area. So P A dx we write as volume. So that's why in case of pressure, the work definition we change to P dV instead of writing F dx because this is more convenient. And work is the energy. So when you move along the direction of pressure, the energy is supplied by the pressure actually. So the work done is P dV. So work done per into volume is only P, and therefore this represents the energy density because energy upon volume is called energy density. So pressure is representing energy density per into volume at a given point. Okay. Similarly, kinetic energy can act as half dm into v square. So dk by d volume, because the dv means volume only, is half rho v square. So this term is also representing energy density, and we can call this as kinetic energy density. Potential is how much? dmgh, and dm can act as rho d volume into gy. So du by d volume, and therefore we can say this is potential energy density. So you can see that there are multiple ways to interpret. So one interpretation is in terms of dimension called height. So we use the word head. Head means height. The other way is, this is the energy way of thinking. This is the energy density, the sum of energy density at every point. So if you add these three types of energy density at every point of the streamline, it turns out to be same, which means if one will decrease, other must increase to balance it out. Understood? Is this clear, guys? What I'm trying to say
Yes,
here.
sir.
So there's a multiple interpretation, and the third is, which is that is something which I like. So this is called, and this is what will help you in solving numerical. This is called pressure head. This is called kinetic head, and now this is called, oh, what I'm saying, sorry. This is called static pressure. My bad. So the concept of pressure which you have studied so far is actually static pressure. And why we are saying static pressure, not just pressure, because the second term, because we are adding to a pressure, so dimensionally it is also pressure. So we have a name for it. We call it kinetic pressure. And the third term we call hydrostatic pressure. And this is always due to the height from the reference. So a proper choice of reference in certain situation may eliminate this value. And what is also important to know that these two terms together, the sum of static pressure and kinetic pressure, in physics we call stagnation pressure. So these are the ways to interpret it. And when I say pressure, then P means the actual pressure, the pressure which you understand. Okay. So when there is a like a airplane, then the lift force is created by the static pressure. Okay. And the velocity of the plane actually creates the difference of static pressure across the wing, or you can say on the two sides of the wing. And because of this difference, the lift is developed. So we all know that there is a shape of the wings of the plane. Have you seen the shape of the wings of the plane?
No.
Okay. So it's a very simple shape. Generally, they keep it like this. This is the cross-sectional view. And now the wings will be like this. Wings are spread like this. Then you have a plane. And I hope now you remember this is the shape of the wing. So this shape is very unique. This shape is very unique. And this shape only matters for everything. So this is called the aerofoil. So what happens if we, and this is generally in the reality it goes down. So I'll just do a flat one. So the airfoils are created like this. And if you look at the Formula One car, if you have not seen, it is available on the New Delhi airport, I think at T3. So even the Formula One car will also use the same airfoil as a spoiler. Now in a car on the back side, we have some fancy design which is called a spoiler, and that is actually meant for the applying the Bernoulli equation. So in a way, so in high speed car, we create the reverse airfoil. So what happens when the plane is moving really fast? So in the frame of the plane, the air will be moving very slow below it. But because of this portion, the air will move like this. So this is like the streamline it will create. And you can see because of the shape, the air molecules will be not present at this location. So the presence in this location is very less. But we have more air particles here. And because the air particles suddenly decreases, so this pressure, which is the atmospheric, of course, this is the atmospheric pressure. But if this pressure is, let's say, P atmospheric, this will be much less than P atmospheric. And the difference of the pressure will actually create the lift. So just below the wing, we have the giant turbine with large wings. And the role of the turbine is to pull the air to create the vacuum. It's like suction pump actually. So it will pull the air, and as the air will come, it will just lift off the wing, but this will be flat here, and therefore the pressure at the upper part of the wing will drop significantly. And this drop of pressure, because I'm not letting the air to come close to my wing, that's how I design my motion. So the absence of air molecules or sudden reduction in the count of air molecules will reduce the pressure, and once the pressure will be reduced, the lift will always be generated, and that is how the plane will keep on flying. Okay, so we have two sides, both sides, we have the turbine on the both sides, and by varying the angular velocity of the turbine omega 1 omega 2, you can vary the lift on the two sides of the wing. So if this lift will be bigger than this lift, it will tilt like this, so the plane can tilt and make a turn. So by varying the omega 1 omega 2 of the two turbines, the plane tilts the wing, and once you tilt the wing, the the air pressure will help you in turning. So now you can make a turn in the sky also. So it is of course because of the air only. So you can see that the basic concept of lift and the omega 1 omega 2, the rotational velocity variation will create the different amount of lift, and you can think of this as a torque, you know? So by changing the force value, I can create a torque. If omega 1 is equals to omega 2, then what will happen? It will remain horizontal, isn't it? So by varying the omega, we can keep on changing the torque value, and once torque will change, it will rotate. So in atmosphere, there are many places where we have the vertical air flow because of the, of course, various geographical factors. So we do have the air flow in the vertical direction, apart from the horizontal flow due to the pressure difference. And this vertical flow is actually present in multiple locations across the globe. And this vertical flow of air creates a turbulence, the air turbulence. So when your flight is passing through certain region, they will indicate that please put your seat belt on, because the plane is passing through the turbulent area, and the turbulent area, the wind pressure on the two wings need not to be equal, so it will start shaking. So although you will try to maintain through omega 1, omega 2, but you will not be able to do so because of the airflow, and therefore there is a sudden turbulence you might have observed during the flight. Okay. In case of F1 car, we want the opposite. So we want that our car should be more grounded. So by creating this flow, the pressure difference is downward. So there is a net force downward, and therefore it will keep the car more grounded, and that is what we need at high speed. So all the F1 cars will have the reverse aerodynamics. So they create the airfall by putting the spoiler at the back in the shape like this. Now in normal car also we have spoiler. Even in Maruti also we have a spoiler, but that is a very small shape, and the reason is generally you don't drive very fast. So these things will only become useful when someone is driving at a really high speed. There the aerodynamics really matters, and it affects a lot of things. So every car will have the spoiler at the back. You can see if you have seen the car. So okay. And the reason is obvious. They need to balance first. The other reason is to minimize the drag also. Okay. So is they spoil the spoiler is called spoiler because the spoiler also destroys the streamline near the back, and hence reduces the pressure difference, because when you're cruising through the air, okay, when you're cruising through the air, we have air drag acting here also. So what happens if the pressure will decrease here because of the shape of the car? If pressure will decrease here, so the pressure force on the car on from right will be more, so it will decrease the mileage also. So what they do is they create a spoiler here at the back. You might have seen something like a tiny shape, and it creates a turbulence. Because of turbulence, the air will be here and it will push from this side, and the net force will be kind of trying to balance, so it will increase the mileage. So a lot of aerodynamics is going on in automobile sector, in pipeline, in petroleum industry when they have to bring the crude oil from the bottom of the some reservoir, and what everything uses is the concept of the aerodynamics. So in the simplest case, we have a motor which also creates a pressure difference, and that's how the water is getting sucked from the bottom to the top of the tank. Everything is happening in certain fashion. Okay. So these are just some motivation why we are learning this chapter. So imagine if you have two pieces of paper kept side by side, like you can hold the two pieces of paper, and if you hold like this parallelly, if you blow the air in between, what do you expect? Will they go away or will they come closer? If you blow the air between, what will happen? Any idea? Anyone saying something? So if you hold the two parallel piece of paper and if you blow the air in between, will they go away or will they come closer? Hello, 1 2 3, 1 2 3. Anyone? Anyone there?
Sir, go away.
Okay, so take paper and do the experiment. Tell me the answer. Take two paper, blow the air. Tell me what you are observing. Everyone, do it quickly.
Where do we have to hold the paper?
Pardon?
So how to hold the paper now?
Hold the paper parallel to your mouth. Keep your mouth, your head in between the paper, like close to your mouth actually. Keep it parallel and blow the air. So keep your mouth somewhere in between and blow the air.
Sir, they are not coming.
Hmm?
Sir, they are not going away from us.
They are going away.
No, not going away.
Blow fast. You can see something. The paper must stick to each other. So the paper will stick to each other. Can you see that?
Yes, sir.
Okay. So why that is happening? They are touching each other. If you blow fast, then they will stick to each other. If you have a two piece of paper kept parallel to each other, if you blow the air like
Yes.
this, they're bound to get stick like this. So imagine that how the concept of pressure comes. So the atmosphere is creating pressure on the paper on both sides. So this pressure is same as this pressure, so the net pressure is zero or net force is zero. That's why you are able to move the paper easily on in air. But imagine you start blowing the air. So the inertia will not hit the paper from both sides equally. So this is being hit like this. But because the air is blown this side, the ability to hit on the wall of the paper because of the forward inertia will diminish and this pressure will become P less than PATM. And the same thing will happen for the other paper. So this side is PATM, but inside is P. And because P is less than PATM, because of the blow which you created, it will be pushed towards each other. Understood? Yes or no?
Yes, sir.
So that is why when the air is moving through the gap, the PATM between the gap which was present actually earlier will reduce by some value. So this will reduce to P value. But the other way of interpreting as per the Bernoulli that the initially we had only PATM and there was no velocity. Now we have the P and we have the velocity. This is how the Bernoulli says that this the sum of all types of pressure for the static and kinetic So the motion of air is something like a kinetic pressure. So whenever the static will reduce, some kinetic will also come into picture. And the sum of the two, which we call stagnation pressure, this remains the same as PATM. So higher the blow or higher the velocity, lesser the drop, like sorry, more the drop, or lesser the pressure, and therefore the paper will come closer to each other. So it is like the loss of one kind of pressure will be compensated by the other kind of pressure. So loss of static is compensated by the gain kinetic pressure. So that is how we think about it. The Bernoulli equation is common sense. You can think this way, that if one pressure will drop, other must rise. Understood? And here the airflow will be horizontal, so we can think as a streamline in the horizontal direction. So the third term will never come into picture, because third term is all about how you write from the reference. So the only first two term will come, but the sum of static and kinetic must be constant. So in the very beginning we had only static, later on we have the static and kinetic, and there's some we can equate, but the wall will be pushed inside or thrown outside, depends on the pressure into area. And this pressure is the static one, not the kinetic one. So when we say pressure into area, although terminology wise we call kinetic pressure hydrostatic pressure, but the pressure which actually exert the force is only static pressure. Understood? So when it comes to calculation of force, then we multiply the static pressure into area to get the force. The kinetic pressure is a way to say that if it is present, it means the static must have dropped. Understood?
Yes.
You can also do the experiment. You can take a paper and keep the page something like this. If you hold the paper on the two edge and keep you near your lips or just below the lower lip, the paper will bend like this, right? Can you do this? Take a long paper, you can take a paper and hold it like this. Is it bending like this? Can you see?
Yes.
Now keeping near the lower lip, try to blow the air by pushing the air below the on the onto the paper.
It is rising.
Yeah, so you can see the bottom, which the hanging part will rise. Why? Can you realize why it is rising?
Yes.
Hmm?
So the atmospheric pressure will
Because
push
the
it up.
air above the air above the paper is now not creating enough pressure. So the on the top part of the paper, the pressure is reduced. Which pressure? Is static. Why? Because we are creating some kinetic pressure by the blowing air. So as the pressure will drop on the top surface, the pressure from the bottom will be more than the top, and so therefore it will push it upward. Understood?
Yes, understood.
Hmm. So many times we all have observed that when you close the door of the your room, the windows of the washroom or other room also start shaking. Anyone observe? So
Yes, sir.
if you observe very, I mean, if you close and open very fast, you can see a strong motion of the window panels. So it is again due to the sudden difference of pressure. Okay. So when you see the high-rise building in which we have the glass wall as a the outer periphery of the building. So when they create the frame for fitting those glass walls, it undergoes tremendous pressure difference challenge. So imagine this is a long building. This is a glass attached. The moment pressure will flow at very high speed, the pressure difference will be created from inside of the building. So this side we have the atmospheric pressure because that's common. But here the pressure will drop. So during storm, what happens? The wind flows so fast that the pressure may drop almost to maybe 1/10 of the atmosphere. And this difference of pressure is really high, really high. So how much is the force? So PATM minus PATM by 10 into area of the window. So they attach some frame inside which you don't see from outside. So they do it in the lab first. So they imagine that what happens in the worst case scenario, if what happens if we create as much pressure difference as, let's say, if the outer surface is having perfect vacuum. So somehow I'm creating the difference by creating vacuum. In that case, the P atmospheric into area, and the P atmospheric is 10 per power 5 Pascal. That's tremendous. It's 1 lakh Newton per meter square. So if we have a glass of 1 square area, you can imagine the force is 1 lakh Newton. Now to tolerate this much force, we need a very strong glass. So in many cases during storm, the glass will tear apart from the building and will fall somewhere. So you might have seen videos somewhere. So also during the storm in small cities, let's say we have shanties, and if the air will flow very fast, then the pressure from the bottom will be so high that it will remove the roof itself, and that happens quite common. So what they do is they put a lot of bricks over the shanties. They don't know about physics, but they have the sense that the air will tear apart the roof. They know this event actually. So they put a lot of bricks to prevent it from flying off during the storm. Understood? So in coastal areas, the storms are very common. Cyclones are very common. So in coastal areas, if we have a building, I mean, of course, we should not create the high-rise buildings. Anyway, dangerous. And if you create, then you have to make the strength good enough. Okay. So there is another way of doing the or deriving the Bernoulli theorem. That's called the energy method. Okay. So you can also see this energy method. Although this method is given in S1, I can see, but let me derive it. So we know that for the flow of liquid in any fluid, the difference of pressure is required. So imagine we have a liquid between this particular cross section. So of course we have the continuous liquid is everywhere, but we are considering only part of it. So what happens if you consider a part of it? So the pressure from this side is acting like this. So this is our system. So I say P1 because these are two different locations. So we also consider this height as H1, this height as H2. Now if you push the liquid slightly inside, if this cross section will go from here to here, this cross section will also move slightly ahead because of conservation of water. So if this is dx1 or something ds1, this will be ds2. But the conservation of volume says that the first cross section area, let's call it A1. So the first thing we can add is A1 ds1 must equals to A2 ds2, right? We are just maintaining the volume. So whatever will enter must
Yeah.
exit because the volume in the given shaded region cannot change. And this is exactly your let's call it D1. This is simple. And if you differentiate with time or if you divide by time, what you get is the continuity equation. So this is exactly this is continuity. Okay, continuity. Now we'll talk about the work done. So if you have a system like this, and if you try to denote the force, then the force will be gravity and the pressure and the normal. But normal will do no work. So we'll find the work done by pressure. And you can see the work done by pressure is pretty much simple. It is P dV because pressure P1 is supporting it, but minus P2 dV because it is opposing it on a system. And therefore, the net work done by the external force is P1 minus P2 into D. Here dV is volume, huh? Just to make clear. So in a way, this is the work done. And the other thing is what is the work done by gravity? Because gravity is also active, which we can show it here. So you can see the system has slightly moved upward, right? Slightly. So work done by gravity is defined as, because gravity is a conservative force, we can act as minus change in potential. If you remember the definition of conservative force. And minus du means the final potential minus initial potential. That's it. So the way to get this is pretty easy. So you can see that the potential energy of the entire system, the difference of the two will be same as the difference of the extra, this volume So if you find the potential of this part and this part, their difference is the difference of the entire system, isn't it? Why? Because whatever is in between will remain maintained, right? So this portion before and after will have same energy, correct? So if this portion will have energy, let's say U1, this is having U2, U, and this is having U2. So the final will be U plus U2, and initial is U1 plus U, right? Do you realize this what I'm saying? Hello, 1, 2, 3.
Yes.
It is clear what I'm writing. So the energy in the last, the potential energy of the entire system will be the U plus U2 in the end, and beginning it was U1 plus U. This is important to understand because other part is common before and after. So what you get is U2 minus U1. That's why I said the potential energy of the elementary part is what we need to get the change, and therefore the work done by gravity will be equals to, and this is how much. The one is mgh dm g h1 minus h2. That's simple answer. Dm is the, so what is dm? This mass. This is d volume. Oh, this is, so dm you can write density into d volume. That's it. Anyway, so we have the work done by gravity. We have the work done by pressure. Is there any other work like normal and all? So answer is no. So what is the work energy theorem? Work done by all force equals to change in kinetic energy. So if the velocity here is v1 at this location, and if the velocity here is v2, so we can write work done by all force equals to change in kinetic energy, which is half dm. And what is the work done by all forces? So we can say work done by pressure, by gravity, and the pressure work done is how much? P1 minus P2 into d volume. And gravity is how much? dmg. If you divide by volume both sides, you will get P1 minus P2. Mass per volume is called density. And what you can realize that this fluid chapter is again the laws of motion in a different symbolic notation. So what we are doing is, because it's fluid, so the mass term we are replacing by the density term. And if you rearrange, you can see that P1 plus half rho V1 square plus rho GH1 equals to P2 plus half rho V2 square plus rho GH2. And if you remember, this is the thing which we derived earlier. So we are proving that the sum will be same at two different cross section. So now we can say the P plus and therefore P upon So this is the statement of Bernoulli equation, that the sum of pressure head, kinetic head, and potential head always remains constant along any streamline, and you can apply between any two cross section. P is the static pressure, okay, and that is the actual pressure which lets the fluid to move. And whenever there is a difference of static pressure, it will result into gain of other types of pressure. So you can say that it is like instead of conservation of energy, it's conservation of pressure. So you can think this way also. So this is like static pressure plus kinetic pressure plus hydrostatic pressure. This is conserved. So the loss of one pressure will result into gain of other pressure. Is this clear? So now, based on this Bernoulli theorem, we can solve numericals. So we have to start with something called the first device called Venturi Meter. So Venturi Meter is used to find the fluid flow in a pipeline. So generally, let's say we have the ONGC or IGL. ONGC, Oil and Natural Gas Corporation. IGL is Incosta Gas Limited, and now we have the Adani and many more. So, and we also have MGL, the Maharashtra Gas Limited, I think, or Mahanagar Gas Limited, sorry, Mahanagar Gas Limited. So they have a pipeline, and because of some reason, the flow is not as per the requirement. So you want to know what is the flow, okay, and how much difference we need to create to maintain the flow. So you check the flow. So such a vast pipeline, you cannot go and dig and find the flow. You cannot dig everything. So what we do is we have some location where you have the kind of opening and closing door actually. So you can open for a while and you can open a small hole. You can just insert this Venturi meter and you can get to know what is the flow rate. And it's pretty easy. So these are glass tubes basically. You can see we have a tube here. Now in both the cross section, the big and the small cross section, we attach a capillary. So now what this capillary will do is the moment you dip this entire into a liquid flow, so let's say this liquid is moving through this and you dip it inside. So what will happen? So you can clearly see that the cross-section area will be bigger on the left side and small on the right side. So at which cross-section we expect a bigger velocity? Right or left? So velocity here is if I say V1 and the velocity here if I say V2, then which one is bigger, V1 or V2? Hello, 1, 2, 3, 1, 2, 3.
Yes.
Tell me at which cross-section velocity is more?
V2.
So definitely because of the reduction in the cross-section area, the velocity must increase because the continuity must be maintained. So the Q is fixed. The first equation we always start solving problem in Bernoulli equation is write the equation of continuity. So first at A1, V1 is A2, V2. So they may give you, they may not give you, so assume. So you always begin like this. Okay. So now at which point the kinetic pressure is more? Tell me. The kinetic pressure is bigger at A2 or A1? Hmm?
A2.
A2. So if the kinetic pressure is more at A2, then which pressure must drop? So out of P1, P2, which should be bigger? So which one is bigger,
P2
P1 or
should be
P2?
bigger.
Which one?
P2.
Sorry. So why P2 will be bigger? If the kinetic pressure is more, then this must occur at the expense of loss of static. Na? If the sum is going to be constant, and if you increase the one term, the other term must decrease, isn't it? And you can see this is a streamline, which is horizontal. So third term is even not required. So what we can say that if I choose this as a reference, the first term and the half rho V1 square, the third term is 0. So the way of saying is the sum must be constant. What does it mean? That if one will increase, the other has to decrease. So there is a gain of kinetic. There must be loss of static. So which pressure will be more, P1 or P2?
P1.
Hmm?
P1.
So to exactly know the fact that P1 is more than P2, we attach these two tubes, and what you will see or observe that the liquid will start rising in the tube. And what is interesting that the liquid will rise more on the left tube. Understand? And the liquid will rise here also, but it will rise less than the, because inside the tube the pressure is really large compared to the atmospheric pressure. You can see a different level of liquid rising in the two tubes, which is an indication that how much is the pressure there. So if I say the if I say the rise as, so we'll consider this. So you can take the rise from the streamline level. So what really matters is the difference that we have to understand. So actual level we don't see, we only see the difference. The difference we can call it delta H. But let's try to write the pressure first, pH, in terms of H1 H2. So what exactly is P1? So we can use the fluid statics, because it's a liquid in a tube. So P1 is nothing but the PATM plus rho g H1. Is this clear? Let's say the PATM is outside pressure. Similarly, what is P2? PATM plus rho g H2. Is this clear? So knowing the
Yes, sir.
P1 and P2, we know the pin P2, and we can see clearly H1 is less than H2. So P1 minus P2 is how much? You can see it's rho g H1 minus H2, and therefore this is rho g delta H. Correct? So the static pressure is always calculated in terms of finding the height of the liquid rise and fall in the tube attached to the flow tube. So flow tube is different. So the purpose of attaching these vertical tubes is to understand how much pressure is actually present there, because otherwise you cannot see the pressure. So there is no way to know the pressure without attaching these tubes. So now, because we know the Bernoulli theorem, we know the pressure relation, we know the continuity relation. Can we solve for the velocity v1 and v2? Can we find v1 v2? No. Yes. Maybe. So you can use 1 and 2, and if you use 1 and 2, what you can add? P1 minus P2, 1 and 2. So P1 minus P2 is nothing but half rho V2 is come as V1 square. If the density of this liquid is rho, this is also rho, because the same liquid will rise, right? And so we can add a rho G delta H. And you can see this is a really nice formula, which is seems like kinematical formula. 2gs V square minus U square equals 2gh. So eventually this looks like a formula of kinematics. Now, because we have the relation of V1, V2, and we know the continuity will also have the relationship between V1 and V2. So by substituting one of them, you can find the other value. So let's try to find the bigger value, the V2. So V2 square minus V1 square, which you can write as what is V1? So V1 will be A2 V2 by A1, right? So V1 equals to A2 V2 by A1, right? This is what I have written. And where I have substituted here. So 4 implies 4A. And once you get the V2, you can find the discharge rate as well. Because we know V2, we can find the V2, which was discharge rate, which is okay. And of course, this will be same as A1. So finding B1 is pretty easy to just substitute. Hmm. If you solve, you can get every answer. Okay. And because you can, if H1 is given, let's say if H1 is given, you can find the actual pressure at P1 also. So you can do every calculation. Understood? So it is pretty easy. Just think in this way. The loss in static is gaining kinetic pressure. So think pressure as a sort of energy, and the loss of one will gain of other. And it is easy to understand that as the cross section will decrease, the velocity will increase. Increase of velocity is same as increase of kinetic pressure, which is same as decrease of static pressure. In fact, any problem in which there is no vertical motion, the third term will never appear. So you can always ignore the third term as long as the streamlines are in horizontal plane. When the streamlines are in the vertical plane, it means when their height is changing all the time, then we have to take a reference and we have to solve the question. Okay, so we'll do a lot of many more problems in the next lecture. I have an lecture in the next 20 to 15 minutes. So okay, I'll do solve most of the questions in the next lecture. So this is the beginning, and theoretically this is sufficient to solve any problem which you want to solve. But I'll show you variety of problem and how to attempt and how to solve. So probably in the next lecture we should finish this chapter comprehensive. All right.